All right. Progress check part B, or MCQ part B, unit 4. We have a situation where we have a spring. This is its natural length, x equals 0. We have an object that lands on it, and then it compresses the spring. They told us in the project or in the problem that this was the 0 line. That was considered the potential energy was 0 at that location, and they want to know which of the following equations correctly indicates the total mechanical energy of the object spring Earth system when it's at position 3. So kinetic energy is 0 because it had no velocity. Potential energy due to gravity was negative because I had gone below the 0 line, which they had defined. And I had a potential energy due to a spring that was x naught squared. There you go. This one, they wanted to know how much work the spring had done, and we need to calculate the area. So 1/2 F naught times X naught. Number 3, which of the following describes the total mechanical energy of an object Earth system, no spring, during the time in which the object is in the air? So this is all related to that first problem. They had 3 questions related to that problem. No spring during the time in which it was in the air and when it was in contact with the spring. So the spring is not a part of the system, so it's doing external work. It has an external force. So when it's in air, there's no spring anyway. And so it's the only two, the object Earth is part of the system, so the mechanical energy has to stay constant. So I can go through and quickly eliminate these. Then I have to look at the ones that say contact with the spring. Well, because the spring wasn't included, the mechanical energy is not constant because I have an external force, which is the spring, because the spring wasn't included in the system. Number 4, I have the situation. I have all frictional forces are considered negligible. Which of the following expression for the cart's initial and final kinetic energy and the cart's Earth system's initial and final potential energy could be used to determine the speed of the cart when it reaches the top? So I have my potential energy initial and my potential energy gravity plus kinetic energy final, and I can use all the heights that I know and find it. Okay, hopefully that one makes sense. This one, negligible friction, the block remains connected, that's fine. We show the force, or I'm sorry, the kinetic energy of the block as it hits the spring. Notice the parabolic path. What's happening to the potential energy of the spring at the same time? It's got to be, because there's no friction, the change in energy must equal 0 because where's the system? It was the, okay, here it is. Spring energy, it's a block spring system, so the spring is part of the system. So energy's got to be conserved. So we're going to have a graph for potential energy due to the spring that's going to be opposite, and the total energy between those two lines has to be the same. So at all times, the total has to be equal to about, I don't know, whatever that is, about 54. So you have to evaluate the table data and confirm that if you took 0 at 0, well, let's use actually 0.3 and 9. At 0.3, if I had approximately 9, and if I added it to whatever that is, approximately 45, that would equal the original mechanical energy. And if you found that table data, that was the only one that works. The rest of them, so this one would be a problem. So this is not an easy problem to figure out. This one for sure is not right. This one for sure is not right. Okay, so you can kind of get close, process of elimination, and then you'd have to actually evaluate some numbers. We are given a speed versus time, and we wanted to know how to determine the work done from 0 to 5. 0 to 5 seconds. Change in kinetic energy equals work. So if I know the mass of the object, I know the speeds, I can find the change. This is always true on an object, okay? Student must determine the work done on an object when an external force is exerted on it after it travels some distance. An external force F is exerted on the object at a position X equals 0 by a string as the object moves some distance d for some time. The force changes such that the force decreases. So we have a decreasing force, so it's not constant. What procedure could be used? We need a graph like this, most likely. These are not easy. I'm just going to tell you right now. But if you can scan and say, okay, graph the force on the vertical axis versus time, force versus time, and then determine the area. That doesn't give me units of work. Graph the position on the vertical axis versus time. Now I have position versus time. The area of that doesn't give me work. Graph the velocity versus time. The area of that doesn't give me work. Graph the force versus position. Force versus position. So my advice on some of these is, you can spend all day trying to evaluate this. I would focus on your answers and see if you can use some process of elimination, because none of those areas in A, B, and C were going to give me units of work. Distance traveled. I have a applied force versus distance. So you can see these distances are approximately the same amount, and the force is approximately the same. Okay, no data is perfect. Which of the following claims regarding the work done? The work done remains constant for each displacement. Work increases. So the work, these are approximately the same little sections. If I wanted to calculate the work under each one of those, I would find the area between each one of those displacements, and they're about the same. Okay. I have number 9. The block of mass M is placed on a semicircle track and released from rest at P. Here's the point. It has a rough surface. So I have some initial energy, and as I move through this pipeline, I'm going to lose energy. I cannot get to the same height because I lost energy. So even though I started off potential energy due to gravity, I've gained kinetic energy at the bottom. I'm going to go back, but I'm never going to get to the same height because I lost some. And every time I go back and forth, I'm going to lose height because I lost energy. So height 2 has to be less than height 1. The block of mass M slides with an initial speed at the bottom of the ramp. This has negligible friction such that H1, it goes up the ramp up to H1. How does the mechanical energy, now we're going to define the system differently, of the block alone, mechanical energy of the block alone. So the only thing the block can have by itself for a type of energy is kinetic energy. So what's it doing as it slides upwards? It's slowing down. So it's got to be losing kinetic energy. So I can immediately eliminate these, okay? And then what's happening to the total mechanical energy of the block Earth system? Well, if there's negligible friction, it has to stay constant. So these were my only two choices there. You haven't had this one, number 11. I'm not going to even talk about it yet because we skipped that section. We'll be back to it very soon. Unit, let's see, what number is this? Oh, that's part of the one that we haven't had. Number 12. The cart of the mass M travels from point A to H1 above the ground to point B. What are we gonna, we have a situation. All I want to know is, did it start, it's nearly 0, so this velocity is equal to 0. So I've only got potential energy due to gravity. Which of the following graphs could represent the potential energy of the cart Earth system at point A and B? Select 2 answers. So I'm looking at potential energy of the Earth cart system. All I know is it decreased from A and B. That is wrong because it did not decrease. This did decrease, so I could have defined my 0 line at point B, so it did decrease. This could be also because I could have defined my 0 line at the bottom of the track. This shows an increase in energy between A and B, and that's not possible. The block is initially slided along a surface with a speed of V naught, a constant force F naught, and then which is exerting on the block. Which of the following figures represents a situation in which the kinetic energy of the block will initially decrease? I have to have a loss of kinetic energy. That means the work done, the change in kinetic energy, has to equal negative work. Okay, so I want this to have a loss. Well, all I have to do is go and evaluate the thetas. Okay, so if I'm traveling to the right and the force is upwards, that angle cosine theta, that's between 0 and 90. That's a positive number. I'm doing positive work, so I'm increasing the kinetic energy. And B, I have a theta between 90 and 180. Plug that into cosine, you'll find that it's doing negative work and it's slowing it down. Kind of makes sense because I'm pulling to the left while it's moving to the right. C, cosine theta, is positive again. I'm doing positive work. D, that theta, no matter which theta you use, will be negative work. It will slow the object down. Excuse me. 14, two more to go, I think. This one, actually, you could define your zero line, two different locations, and based on that, you will end up with one of these equations. Okay, both of them start with an initial velocity of 0. Both of them had uh, potential energy due to gravity based on your height, and we could assess it that way. So that's that problem. Number 15 is a difficult problem. I've never been good at these, nor has most students. I know that you're at a somewhat of a disadvantage because of lack of hands-on labs, but I'm just going to tell you these would have been hard even if you did hands-on labs. We must perform an experiment to do work. We want to find two things. So if we had a force sensor and we could move this block to different locations that we could actually measure the force that the spring was putting on the block versus distance, we could form a force versus distance curve and calculate the area. This one is also a little tricky. We have a situation where which of the following conclusions can be drawn from the data? I actually probably would not. I mean, I actually didn't know. I haven't looked at the answer. I mean, the answers are right here. But how I would have done this is I know that the change in kinetic energy has to be equal to work done by that force, this force applied. Okay, so what is the work equal to? The force applied times distance. I can evaluate the change in kinetic energy and compare it to that force and distance, and you'll notice they're not the same. So the total mechanical energy after the given trial is equal to the kinetic energy. That is true. That's always true. The total mechanical energy is equal to the kinetic energy. That is true. Okay. We know that there has to be an external force because these don't equal one another. So something is going on. Because this force right here would give me a different kinetic energy. Okay, it would give me more. Is that right? Yes. Yep. There had to be something probably slowing it down, like force of friction. Excuse me. Okay. I know they're not easy, guys. But I'm sometimes feel like these progress checks are kind of far out there. But anyway, okay. I am open for questions. If you have any, I'd be happy to go through it even more in depth if there's one in particular that's got you stumped. Come see me.